Okay, we go to the last speaker of today in this session. It's Paul Esslinger from the Pacific Northwest National Laboratory. He's not here,
Thank you,
but the presentation will also be given by Dr. Carolyn Seifert. Please go ahead.
Great, thank you for that great introduction. I'm Paul Esslinger. So actually, I think this is a great follow-on to the presentation that we just saw. Paul's been doing a lot of work, as many of you know, in how we estimate source parameters in the presence of nuisance backgrounds, right? Specifically explosion source parameters. And so what I'm going to present today is some work that Paul and Ramesh and Brian have done over the past couple of years to explore this ability, this algorithm that they've developed to calculate source parameters when you know you have nuisances and you know where they are. So let's sort of start here. I think I've said most of this. We know most of this. Let's see. Here, what we're doing is we're taking a simulated data set that has 384 synthetic release events, synthetic nuclear explosions, if you will, that are each releasing xenon-133. And the question here is using this algorithm that takes into account the presence of nuisance sources, even if you don't know the quantity being released from those sources, you know where they are because they're fixed in space and you have knowledge of them. Can you still reconstruct your explosive source term in that presence? And then is there a threshold below which the release from the event you care about is masked by these nuisance sources with this methodology? So what the team did was to model a series of explosions at various locations, in this case in southern Nevada and parts of California. The reason I guess we're focused here is this work was part of a larger virtual experiment in multi-phenomenological signatures of nuclear explosions. So a number of these sites are of the simulated nuclear explosions are sites where there were actually mining events or other chemical explosions that had seismic signatures that other members of our community could use. So on the left we have the green sites, which are the explosion sites, the two nuisance sources. There's a simulated medical isotope production facility in sort of the northwest corner and a nuclear power plant in the southeast corner. And those were placed in those positions because in this part of the United States, the preliminary or primary wind conditions are such that they either come from the southeast or the northwest. And so if you put your nuisances there, they will generally flood the field. And then on the right, we have a very dense network of radionuclide stations, again, co-located with seismic stations in this case for this multi-phenomenological analysis. And the team simulated the releases, a number of releases from those 7 green locations, plus the 2 nuisance sources, and did forward ATM to calculate the response on all those sensors. The Met conditions were such that essentially using 4 10-day periods of actual weather data from summer and winter, so over the course of like 18 months. And then the sample concentrations at each of those stations were developed using a high split model, using high resolution WRF runs. And to answer the resolution question, we're at 900 meters in 15-minute intervals. And so that's sort of the time forward. How do we get to concentrations at those stations? And then the source estimation process, which takes those measurements and back calculates to the estimated source quantity of the explosion term, is done also using high split, but in this case we're using NOAA's high resolution rapid refresh MET data. And so this is how we're producing the analysis. The releases themselves are drawn from these distributions for the actual explosion itself. So what we have is a range from roughly 1 to 100 tons of explosive yield, and 3 different times at which the xenon was separated from its precursor. So we sample through all these, pick a specific scenario, and then run that. The total releases that are represented here are about 10 to the minus 4 of the total xenon-133 that's produced. So you may have seen in a paper that Paul produced in 2019 this Bayesian framework to do the source estimation in the presence of nuisances. I encourage you to go reference that paper for details on the methodology. But essentially what it can do is to reference or to estimate releases from 2 nuisance facilities. Again, you know where they are, but you don't know how much they're releasing. And then you search for a single nuclear explosion somewhere in there with an unknown release time, duration, location, and magnitude. We don't know anything, but we think there might be something there. And then it uses about a week's worth of data at a time to kind of search through and see, can I see something in addition to the 2 nuisance sources that I'm aware of? So after many, many ATM runs, I'm told it was something like 6 weeks on a high-performance computing cluster to get through all of the ATM runs for this analysis. We've got 384 release cases that were run on that very dense network of 84 samplers. And of those 384 cases, 254 actually had source terms that could be estimated. Now this is if you don't include any background and you're just looking at how much xenon-133 gets from your emission point to samplers. Of those 384, 7 were basically all 0 concentrations. Basically the wind went outside the network. 123 had concentrations that were present but less than the MDC from the explosive source. And that leaves us with our 254. 40 of those were 1 detection and 214 with 2 or more detections made in the network. When we add in the background emissions from the nuclear power plant and the medical isotope production facility, what we see is that the nuisance sources contribute somewhere between 5 and 28 millibecquerels per cubic meter to the maximum samples, maximum activity of the samples, depending on which week of ATM that we actually use for that. A really important point about this data set is that in 30% of only 30% of the cases does the amount of xenon from the explosion be greater than the amount of xenon from the nuisance sources, okay? So in 70% of the cases, the nuisance sources provide a greater contribution to the highest collected sample, okay? So what happens when we run through the model? This is using all 84 samplers. And one of the things that Paul and company did was they took the results and they divided them into a couple of bins. So of those 254 cases in which at least 1 sampler got a detection, if you then say, okay, well, how many got at least a 0.5 millibecquerel per cubic meter measurement, or a 1 millibecquerel or up to 10 millibecquerel. So how many cases is that true for at least 1 station in the network? And then look at the distance error calculated with the method in comparison to the actual explosion location under the various conditions, or the magnitude error or the timing error. So that's really what's shown here. And not surprisingly, the higher the concentration from the explosive source, the lower the distance error is. I think that's what you see here on this first graph. The second one is that the magnitude error is actually not that different across the cases, and the timing actually looks fairly good, although you'll see sort of that low side tail at negative numbers, and that's really because when the explosive contribution to the measurement is very, very small, the fluctuations in the nuisance background tend to dominate, and it's hard to tell the timing of within the week of data that we're looking at. Here's what happens when you take 84 samplers and downsample them to 8. And in this case, these 8 were selected based on having the most detections, essentially. And so if you look at these 8 samplers in comparison, what you see is the distance errors, of course, go up. You have less data on location. That the magnitude errors in this case are now biased high. And it's not entirely clear why that's true, but it was something that we observed, and then our timing errors also become shifted in that way. But what we find is that having at least one sample with an increment of at least 5 millibecquerels per cubic meter from the explosive source does help overcome the obfuscation from background sources. So there's a lot here, I recognize, but I'll just say in summary, it is possible to estimate the release characteristics, the timing and the location and the magnitude, even in the presence of nuisance backgrounds, these power plants and medical isotope production facilities, and even when you don't know how much they're producing, but you know where they are. And this provided an opportunity for us to test out that algorithm on a different data set. That some of these release events may even be detectable, even though they're smaller in magnitude at the sampler than the contribution from the nuisance sources. So it's, I think, really an important result to understand that even though we may be in situations where certain stations are overwhelmed, it may still be possible to find an unknown explosion source in that scenario. Thank you.
Thank you very much, Carolyn, for providing this ATM study by Paul Esslinger. The room is open for questions. Can we have a microphone? Here in the front.
For Christian.
Oh, sorry. Yeah, thank you very much for this nice talk. I always like to hear about results from Paul and his group. So one comment, and you already pointed somehow towards this. So when you showed the slide where you did a reduction from 40 to 8 samplers, I think. So I think what is still in favor in your study is the high sampling density and the low transport ranges. I mean, it probably looks quite different, the performance, if you consider IMS transport ranges and the sparseness of the IMS.
Yeah, I think that's an excellent point. This was a high spatial density network, and even higher than, let's say, some of the other networks that we see, for example, in Europe. So I think this is important. The other thing I'll note is that because we were had such a high spatial density, the emission you might have noticed from the medical isotope production was fairly small for what you would expect. And I think that really was a artificiality of this, let's say, close-in network.
Other question?
Thank you, Corey. Very interesting. I know you don't want to speculate, so you didn't know, but I'm very curious about when you have the 8 samplers and you overestimate the magnitude. And I would like you to speculate a little bit that. Is that because you see the background sources as explosions, or maybe you don't know, but it would seem very interesting that you get such a bias on the magnitude?
Yeah, I can't say. I'm sorry. I don't know. Mm-hmm.
more questions? Okay, then we end this session. Carolyn, thank you for a
you.
great discussion, also from online viewers.